Welcome to the second week of our course in mathematics. Today we are going to deal with one of the topics that we had last week. Problem was, you remember we developed the characteristic polynomial to determine the eigenvalues of a matrix. And the problem there was, it might well happen that these characteristic polynomials did not have a real root. So today we're going to develop a solution for that by introducing a new number system, the complex numbers. And that is going to be our chapter 11.4, complex numbers. Okay, so remember the problem. That we faced was the question of, do all matrices have eigenvalues and eigenvectors for that matter? Do all matrices have eigenvalues? And to see a small example of that, let's have a look at the following matrix. A is the matrix 0, 1, minus 1, 0. Now if we compute the characteristic polynomial of that matrix, what we get is PA of lambda is the determinant of minus lambda, 1, minus 1, minus lambda. That determinant can easily be computed. That is lambda squared minus minus 1, so plus 1. And as you can easily see, this polynomial does not possess any real roots, right? So that is greater or equal to 0, or more specifically, it's even greater than 0. So PA of lambda does not possess any real roots. So we don't get eigenvalues in that case. Now what can we do about this? Well, one possible solution is to just extend our set of numbers. We are currently working on the set of real numbers, and polynomials like this one, lambda squared plus 1, just don't have any roots on the real numbers. That's because there is no real number that becomes negative if you square it. So in that case, we would need a number with the property lambda squared equals minus 1. Now you can imagine, of course, this problem did not appear only in the context of eigenvalues and eigenvectors. That appeared a lot earlier in mathematics. And some creative minds find a way out of that by simply extending the number system. It's not as easy as it sounds, actually. You cannot just simply extend the number system and then expect it to behave. But in this case, it turns out there is a way to extend the known number system so that we can actually get square roots of negative numbers in a way that is consistent with how we do computations, how we do arithmetic over the real numbers. And that is what we'll do just now. So what we need to do is we want to extend our field of real numbers such that there is a number with the property lambda squared equals minus 1. And then we could have roots to that polynomial above. So let's first see the formal definition, and then we'll see how to work with these numbers and why what we wanted to do actually works. So here's the definition. The set C, and we abbreviate that with a C for complex, of complex numbers is the set R times R together with the following operations. So what we do is basically, instead of just taking one real number, we take pairs of real numbers. We will later use the names real part and imaginary part for the first and the second component of those pairs. And now we're going to define an addition and a multiplication on those pairs. Okay, so first the addition, that one is straightforward. So if we have a pair alpha beta, and we add another pair gamma delta, then adding these parts together just works component wise. So we just say, well, that is alpha plus gamma and beta plus delta. Okay. Secondly, we will also need a multiplication, and that one is not that straightforward. It turns out we cannot just do it component-wise. That will not achieve the goal that we want, and that will not yield a usable number system at all. So what we're doing here is, again, we take two pairs, alpha beta and gamma delta, and we multiply those. And we do this in the following way. So the rule here is the product of these two is alpha gamma minus beta delta. And the second component is alpha delta plus beta gamma. Well, that sounds complicated. But in a few minutes, we'll get to know a convention, an abbreviation that makes dealing with these rules pretty straightforward. So no need to actually remember that rule. I'll tell you what to remember in just a minute. Okay? So let's just complete that definition by remarking that C, the set we get this way, is an algebraic field, which means the usual rules of arithmetic known from R also apply here. C is an algebraic field, meaning the usual arithmetic rules known from R also apply to C, right? In particular, distributive law applies for C. The multiplication and the addition are commutative, so you can exchange the order. Basically, you can compute over C same way as you can compute over R. The only difference is you can't compare numbers anymore. So over R, you have an ordering. You can say one number is smaller than the other. Over C, that is not the case anymore. You can, of course, say when two numbers are equivalent, but there is no smaller or larger anymore over C. That will become more apparent when we see the visualization in the next video. But let's first talk about notation and the rules for computing with numbers in C. And there is a nice convention that makes life a lot easier here. So we'll introduce that now. We abbreviate the following. Instead of the pair 1, 0, we just write 1. And instead of the pair 0, 1, we just write I. And I is the so-called imaginary unit. Okay, and if we do that, then we can just write a complex number as a sum of those two. So a complex number Z equals alpha beta can then be written as, well, following form: Z equals alpha beta, and we can write that as alpha times 1, 0 plus beta times 0, 1. And that's the same as, well, alpha times 1 plus beta times I. And then we'll also apply the convention. We usually don't write the real 1. So we just write alpha here. And the I usually goes in front. So that's alpha plus I beta. And that is, in fact, the usual way to denote complex numbers. You write those both parts as a sum, and you use the I to distinguish the real first part and the imaginary second part. Okay, and then there's just one more thing that we need to know, and that's how to compute with this I. So with I times I, you remember I was an abbreviation for 0, 1. And now if we just once apply this complicated rule of multiplication that was in our definition, what we get is the following. So let's scroll back a little to see how that works. We have alpha gamma, so we first multiply the first component of those numbers, minus beta delta, so minus the second component of those numbers. So what we get here is, well, the first is 0, so it's 0 times 0, minus, and the second is 1, so 1 times 1. That's the real part. And for the imaginary part, we get alpha delta plus beta gamma. So this is the mix, right? So we take the first component of the first number multiplied by the second component of the second number, and vice versa. So in this case, that'll give us 0 times 1 plus 1 times 0. So that's minus 1, 0, or just minus 1. Okay? And if we just use this rule, we can work almost as we used to with real numbers. We can work with complex numbers almost as with reals. Now, instead of boring you with a bunch of rules, I'll just give you a few examples to see how you work with complex numbers. Okay, so let's see about a bunch of examples here. First one, very simple one. Let's do a multiplication the new way. Let's say we have something like 2i times 3 plus I. Now if we just use this I as a constant, what we get is 2 times 3i, so that's 6i, plus 2i times I, so that's 2i squared. And remember, I squared is minus 1. So what we get is 6i minus 2, or if we just reorder that, minus 2 plus 6i. Okay, so that's how you work with complex numbers. A little more sophisticated, let's say something like 2 plus I times 4 plus 2i. If we do that multiplication here. Okay, what do we get? We get 2 times 4, that is 8, plus 2 times 2i, that is 4i, plus I times 4, so 4i once more, plus 2i squared. Again, I squared is minus 1, so 2i squared is minus 2, and 8 minus 2 is 6, so we have 6 plus 8i. Okay. One more example, of course, you can also divide by real numbers, so by complex numbers, sorry. So how about something like 1 over I? Can you express that in the usual form? And of course you can. So the trick here is to get the imaginary numbers out of the denominator. And what you do is you simply multiply, or you simply extend the fraction by a suitable number so that the denominator becomes a real number. In this case, that's easily done. You just have this 1 over I, and we multiply both numerator and denominator by I. And what we get then is I over I squared. So I over minus 1, and that is just minus I. Okay? And one more example makes this takes this a little further. If we have not just an imaginary unit, but a complex number like alpha plus I beta in the denominator, what can we do then? Well, same trick almost. If we want the denominator to become a real number, what we do is we extend our fraction again, and this time we use alpha minus I beta. Okay, doing that, the numerator becomes alpha minus I beta, that's okay. And the denominator becomes alpha squared minus I squared beta squared. And again, with this I squared, the imaginary unit is gone. So we have alpha minus I beta over alpha squared plus beta squared. Okay, so again, we have a rational denominator. And that is something that you usually want to be able to separate the real and the complex part properly. Okay, we conclude with just a few more definitions, just to define some names. Basically, definition. Let's say we have a complex number. So for a complex number, Z equals alpha plus I beta, we define the following. First, I already said this, the two parts of Z, alpha and beta, are referred to as the real part and the imaginary part of a complex number. So the real part, abbreviated as RE of Z, that is simply alpha, is the real part, offset, and the second one, abbreviated as IM offset, is better without the I. That is the so-called imaginary part. Offset. Okay, then there's one more operation for the complex numbers that we don't have for the reals, and that is the so-called complex conjugation, denoted by just writing a bar over the number set. That is alpha plus I beta conjugate, and that is simply defined by replacing the plus before the imaginary part by a minus, right? So this is the complex conjugate of set. Is called the complex conjugate of that number set. And finally, absolute values. Of course, there's also an absolute value for numbers in set. And one important property of absolute values is that they remain positive or about 0. So we have to define those in a way that makes sure the absolute value of a number, a complex number, is non-negative. And that is done by the following operation. We take the number itself, we multiply by the complex conjugate, and then we take the square root. And what that does is basically just see that. So what we have here is alpha plus I beta. We multiply by alpha minus I beta. Well, what do we get? We get alpha squared minus I squared beta squared. Minus I squared is plus 1. So that's plus beta squared. Okay, that is called the absolute value of set. And you will notice that this absolute value of set is the same as the norm of the vector alpha beta. So basically, if you say, well, a complex number is basically a vector with 2 components, then the absolute value is just the length of that vector. So that's how that is defined. And that leads us into the next part, which will be dealt with in the next video. We'll have a brief look at how to visualize complex numbers, and I just gave you the basic idea here, and that is simply to regard a complex number as a vector of 2 components. So you can visualize each complex number as a point in a 2-dimensional plane, and that's just what we're going to do.